Okay, so in this video we want to talk about higher order derivatives. So first, what I want to give you, this is from the notes, a little bit more of a quick rundown of the idea of what we mean when we say higher order derivatives. That just means taking the derivative more than one time. So if we apply it to a function two times, notation would be f double prime of x, and that would be called the second derivative. And there's two really common notations that we use for derivatives, whether it be a first derivative, a second, or anything higher. And that is our function notation, and that is what are sometimes called our operator or slope notation, because it's written as a fraction like slope. Because remember, slope is a rate of change, so it's change in y over change in x. So of course, first derivative, f prime or y prime, and then dy dx. Second derivative, f double prime of x, and then the notation we use is d2 with the superscript on the d and a superscript on the x. So d2y dx2. If you eventually go on and take calculus 3, where you deal with multiple variable calculus, this notation dx2, dx3, and so on will have a little bit more meaning. For now, that's just a notation. When we go up to the third derivative, we use three little tick marks for f triple prime. And then third derivative kind of follows the same pattern. And for anything above that, it's just dny dxn. Fourth derivative and up, we don't make tick marks. Can you imagine someone asks you to do the 21st derivative and you have f followed by 21 little tick marks? That gets a little tedious. So beyond that, we put the number in parentheses. And so fn of x is the nth derivative. And of course, we have dny dxn, the other slope or operator notation. So now that we've talked about our notation for derivatives, let's just look at some examples of finding some higher derivatives. So in this case, we're given the function f of x equals 6x to the fourth minus 5x squared plus 12x. And we're asked to find the sixth derivative of that function. So that means we need to start with the function. We're going to differentiate it. That will get us the first one. Differentiate that answer. We're going to keep doing that 6 times. So first things first, f prime. So using our power rule, that'll be 6. Bring the 4 down. 6 times 4 is 24. Drop the exponent, x cubed. 24x cubed. For 5x squared, bring the 2 down. 5 and 2 is 10. Drop the exponent, so we get minus 10x. And then finally, derivative of 12x is just 12. And then we differentiate again. You may want to pause the video and try to work this out the rest of the way yourself. So the second derivative, we bring the 3 down. That gives us 72. Drop it to x squared. Derivative of 10x is just 10, minus 10. And then derivative of 12 is 0, so it's gone. Third derivative, bring the 2 down. We get 144. Drop it. We get x. The 10 goes away because it's a constant. Fourth derivative would just be 144. Fifth derivative would just be 0 because it's a constant. And of course, derivative of a constant is 0 and so on for the rest of its life. The higher derivatives from 5 and up for this function will always going to be 0. And that's a unique property of polynomials, that there is going to be some derivative level where it'll all just start becoming 0 from that point onward. Let's consider another example here. 5 over x. 5 over x. And this time we want to find the third derivative. The third derivative. Okay, so first things first, 5 over x, we should rewrite as 5x to the minus 1. That way we can use our power rule. And then we just use the power rule. So multiply by the exponent, drop it by 1. That'll be negative 5x to the negative second. No reason to worry about getting rid of the negative exponent there. We'll just stick with that. Okay. Take the derivative again, multiply by the 2. That gives us positive 10. Drop it, x to the negative third. And then one more time, multiply by the negative 3. The exponent gives us negative 30. drop it by 1, x to the negative fourth, and then finally we get rid of the negative exponent by moving to the bottom. We get negative 30 over x to the fourth. Okay, one final example here. Here I'm using the operator notation. I'm doing the fifth derivative of that stuff with respect to x 5 times. So of sine x. Well, we've shown earlier in a previous video that derivative of sine is going to be cosine. And I'm giving you a little note here. This is something you're going to prove as a turn-in problem, that the derivative of cosine is negative sine x using the limit definition. So we're going to use that in this problem. So the derivative of sine, of course, is cosine. And then as I've just told you, the derivative of cosine, so the second derivative, will be negative sine. And so now I'm back to doing the derivative of sine. But we know that the derivative of sine is just cosine. So the third derivative, which would be the derivative of negative sine, will be negative cosine. But now we know the derivative of cosine is negative sine. So the derivative of negative cosine will be negative sine, which will just be positive sine. And then we just do one more derivative because we need to do the fifth one. So we differentiate sine again, and we get back to cosine. So notice that the sine function, its derivative repeats. You're back to where it starts on the fourth time through. You're back to where it starts on the fourth time through. You may think of something else that behaves like that. And that is your imaginary number of I. It cycles on a period of 4 times. And it turns out there's actually a connection. There's actually a little bit of a connection between the sine and the I. There is a little bit of connection, the way that they connect, and you learn about that in calculus 2. Okay, so those are higher order derivatives. Until next time.